Okay, let's get started, please. So today we're going to go finally into section 8.2 after spending an interminable time in 8.1. 8.2 is about series, okay, so-called infinite series. Okay, and infinite series are basically, you can think of them as a special kind of sequence. It's, this will give us the answer. Well, it will give us the right way of dealing with sums of infinite sequences. Okay, so remember I showed you something bizarre, that if you looked at 1 minus a half plus a third minus a fourth plus a fifth plus a fifth, etc., and you weren't careful about what that meant, then you could end up in some real trouble. Right, really significant trouble that would cause you to doubt, what numbers really mean at all, right? This is how mathematicians found a way to deal with these sort of infinite sums in a consistent way. Okay, this is the answer. What we're going to talk about today. Okay, and it's based on what we did before. Okay, so before we do anything, we need to introduce something called sigma notation. Okay, that is something like this. If I write summation, so you have some sequence, so a sub n, a sequence. Okay, so you start off with a sequence, and then we have something that we write big sigma a sub n, say, from n equals 1 to k. Okay. How many of you already know what this means? Okay, then we're in the right place. Then we're doing the right thing. Okay, so this, when we write something like this, this is a sigma, right? Sigma, capital sigma. This is a lowercase sigma, in case you are curious. This sigma stands for sum. This S, sigma is an S, it stands for sum here. Okay, and so we're summing, what this says is sum the a sub n's. This says the sum of the a sub n's from n equals 1 to n equals k. Okay, so that's how you read this in English. Right? This is the sum of the a sub n's from n equals 1 to k. Okay. In other words, it is a1 plus a2 plus a3 plus up to a sub k. Okay. Right? Notice that the index can be changed. Right, we could write summation a sub j from j equals 1 to k, and that would be the same thing. Right, the sum of the a sub j's from j equals 1 to k, that's the same thing as sum of the a sub n's from n equals 1 to k. Right. It's just like in when you're integrating, right? If I integrate f of x from x equals 1 to 5, I can change the, that's exactly the same thing as this. So this is just your dummy variable, right? You've got your dummy index. Okay, so just to give some examples, if I write summation of this way, a sub I equals I. Okay, save the sequence a sub I equals I from 1 to infinity, right? And if I write summation a sub I from I equals 1 to 4, what is that? Well, that would be a1 plus a2 plus a3 plus a4, right? Which is 1 plus 2 plus 3 plus 4, right? Okay. Is that okay? Making sense? Makes sense to everybody? Anybody have questions so far? Anybody confused? Hey, you okay? Yes? Okay. So I should say that we often, just for shorthand, we'll write it like this. Summation of I from I equals 1 to 4. Right? Instead of writing a sub I equals I and writing summation a sub I, you could write summation of I from I equals 1 to 4. Okay, that's the same thing as 1 plus 2 plus 3 plus 4. Right? Because you're summing, this, if you write this I here, this means that this is the element of your sequence. Okay. If I write summation 2 from I equals 1 to 4, what does that mean? What do you think that should mean? Well, it means that your sequence is just 2, right? A sub I is 2. So you just add 2 plus 2 plus 2 plus 2. Right? So this is 8. Right? 2 plus 2 plus 2 plus 2. Does that make sense? Right? If I sum the number 2 as the index ranges from 1 to 4, right? At time 1, I add a 2. At time 2, I add a 2. At time 3, I add a 2. At time 4, I add a 2 also. Right? So I get 4 2s. Okay. Right. If I write summation of I from I equals 3 to 7, well, I'm just going from I equals 3 to 7. Right? So 3 plus 4 plus 5 plus 6 plus 7. Right? So 3 plus 4 plus 5 plus 6 plus 7. That is, I don't have to start at 1. Right? I could start at some arbitrary number. I could start at some arbitrary number. I could start at -5. The numbers from -5 to 10 or something like that. Okay. Right. If I write summation I from I equals 1 to n, what's that? What does that mean? Somebody just read it in English. What would I write down for that? Anything.
You keep adding i's until it gets to n.
Yeah, so what do I start off with?
It'd be 1 plus 2 plus 3 plus
1 plus 2 plus 3 plus all the way up to n. Right? Does anybody know the formula for this? The sum of numbers from 1 to n? Maybe this is something you learn in elementary school and then forget it afterwards. Hannah?
It's like 1 plus n times half of the n.
Yes, exactly. Yeah. N times n plus 1 over 2. N times n plus 1 over 2. There's a formula for it. So like, if you were asked to add the numbers from 1 to 100 in elementary school, you wouldn't have to do it. You would just take 100 times 101 and divide that by 2 and get 5,050. Actually, that's the story behind this formula. Apparently, the greatest of all mathematicians, Gauss, when he was 8 years old, was in class, and his class was being really noisy, and the teacher got angry and said, okay, you kids, your assignment right now is to add the numbers from 1 to 100. And while all the other kids were, laboriously adding, Gauss was sitting back and thinking, and then he wrote 5,050 on his tablet and then handed it in. So apparently he had figured out how to do it in that 1 minute as an 8-year-old. They say that when Gauss was an old man, he liked to tell this story about his childhood. So there's a lot of stories about mathematicians that are probably false, but this one seems like it was true. Right? There are a lot of jokes or stories about mathematicians, amazing ability that probably are not exactly true. But this one seems like it was true.
wasn't it when you went from 0 to 100? 100 plus 0 is 100 and 1 plus 99 is 100, and if you keep going Equal 100.
Yeah. So you can say 1 plus 2 plus 3 plus 4 plus 5 up to 100. If you add the same thing to itself in the reverse order, right, then you get 101. Right. So right. So if you add, your sum plus itself is 101 100 times, right? And then you have two of your sums, so you divide by 2. Yeah. Okay. I'm just resisting telling you some stories. I'm trying to hold back from telling you some joke or story. Okay, in the interest of time. Okay. Okay. Just for your amusement, although this is not as amusing as a story, the sum of squares from 1 to n also has a formula. It's n plus 1, 2n plus 1 over 6. Sum of cubes has a formula, etc., etc. Okay, so everybody getting a sense of, what sigma notation is? Like, how you can use sigma notation? Let me just say one thing, and I'm not sure we're going to need this, but you can, if I take k equals 1 to n, I can rewrite this as, say, j minus 4 squared from j equals 5 to n minus 4. Right? You can do it, you can shift the index. Right? So what I'm doing is I'm saying let j equal k plus 4. Right? Let j equals k plus 4. Okay. This is going to be the same thing, right? Because j goes from 5 to, I'm sorry, this should be n plus 4. J goes from 5 to n plus 4, right? So the first thing is going to be 1 squared, and then the last thing is going to be n squared. Right? I hope you see that these are exactly the same thing. I've just shifted the index for some reason here. Is that clear? Everybody see that? Yes, sure. Right, so here what I have is k squared from 1 to n. K goes from 1 to n. So this is 1 plus 2 squared plus 3 squared plus n squared. Right? I'm rewriting this in a more complicated way for some reason. You might need to do this at some point. Okay. Instead, I'm taking my index to start from 5 and end at n plus 4. Here my index started at 1 and ended at n. Now I'm going to create a new index that's 4 greater than the other. Okay, so it'll go from 5 to n plus 4, right? And I'm going to sum j minus 4, because j minus 4 is k, right? J minus 4 is k, right? So I'm summing, k squared from k equals 1 to n, but I've just written it differently. I've got exactly the same sum. Okay, so I can't resist. I'm going to tell you one funny story that I heard when I was a freshman from my TA. He said that this is a story about a mathematician at MIT in the 30s who was famous for his absent-mindedness. And the story goes that, let me make sure I get it right. So this mathematician's named Norbert Wiener. He's in, very famous mathematician. And the story goes that one day, Norbert Wiener has moved from his home of many, for a long time. He's moved from his home of many years to a different place. But that, he forgets that he has moved. So he goes back to his old house, and he's like, the house is empty. Right? He's confused. What's going on? Doesn't see anybody around. Finally, he sees a little girl sitting around there, and he says, little girl, what happened to the family that used to live here? And the girl says, Mommy told me to wait here for you, Daddy. So, okay, anyway. So he was so intent on his problem that he didn't realize that it was his own daughter he was speaking to. Anyway, but again, I've heard that Norbert Wiener's daughter said that this is false. This actually didn't happen. But yeah, when I heard it, I thought it was true. Okay, so now that we've got segmentation down, we want to okay, so we introduce something called the sequence of partial sums. Okay. So here's the definition. So you start off with a sequence, AK. So let this thing be a sequence, an infinite sequence. Okay. We define the sequence of partial sums the sequence S of k, let me say S of n, the sequence S of n of partial sums of your first sequence. Okay. By letting S of n be the sum of the a sub k's from k equals 1 to n. So let me give you an example. If I have a sub n as 2 to the, if I have a sub k as 2 to the k, okay, k equals 1 to infinity, then S1 is the sum of the first, the sum from k equals 1 to 1 of ak. S2 is the sum from k equals 1 to 2. S3 is the sum from k equals 1 to 3 of the a sub k's. The sum of the first element, the first two elements, the first three elements, and so on and so forth. Okay? So you sum, right? S of n is the sum of the first n elements of the a sub k. Take a minute and write down the first four elements. What do these actually equals what? Equals what? Oh, actually, sorry, this should not be 2 to the k, but 2 to the negative k. Sorry. In other words, 1 over 2 to the k. turn to somebody nearby and talk with them? Okay, so what is this? Maybe this is too easy. What is this? The first one is just a half, right? The second one is 3/4, right? It's a half plus a fourth, right? In other words, 3/4. This next one is half plus fourth plus an eighth, right? Which is what? 7/8, right? 7/8, right? And maybe you see the pattern, right? What's S sub n going to be? Well, it's going to be 1/2 plus fourth plus an eighth, all the way up to 1/2 to the n. Does anybody see what that's going to be? If you think about it sort of geometrically, the first one is you go halfway to 1, right? That's 1/2, right? And then in S2, you go halfway to 1, and then you go another halfway to 1, right? You add on a fourth, right? You add on a fourth, you get 3/4, right? That's your second partial sum, right? Okay, what's the nth one going to be? It'll be 1. So you can think of the second one as 1. Do I need to offer a bonus point before anybody will tell me the correct answer? Yes, Marie Claire.
The sum would be 2 to the n minus 1 over 2 to the n.
2 to the n minus 1 over 2 to the n. Yeah, that's right. That's right. So yeah, I mean, if you see the pattern, we'll get to this more carefully in a second. But what you see is that, the first one, you add a half, and you're half away from 1, right? Your distance is half away from 1. And then you add on a quarter, right? And your distance from 1 is a quarter now, right? The third one, you add on an eighth, and your distance is an eighth away from 1, right? By the time you get to this guy, well, you are 1 over 2 to the n away from 1. Okay. Okay. So, what do you see about this S of n? Well, as n goes to infinity, what happens? As n goes to infinity, what do you get? The partial sums converge to 1, right? The sequence of partial sums converges to 1, right? The limit of the S of n is 1 as n goes to infinity. Okay, so, okay, let me say this again. We started with a sequence, right? With this sequence, 1/2, 1/4, 1/8, 1/16, 1/32, and so on and so forth, right? And then we looked at the sequence of partial sums. We said, let's sum all the terms, the first term. Let's sum the first 2 terms. Let's sum the first 3 terms, the first 4 terms, et cetera, et cetera. And we look at those guys, right? This is called S1, S2, S3, S4, right? And what we see is that if we look at the sequence of partial sums, that sequence of partial sums converges to 1. Okay? This is how we think about an infinite sum. Okay? So we say what we write is that we write that the sum of 2 to the minus k from k equals 1 to infinity equals 1. Okay. Okay. When when the sum of the partial sequences turns out to be some number, we say that the infinite sum is 1. Okay, let me come back here and put it into the definition formally. Okay, so you start off with an infinite sequence. You create the sequence of partial sums. Okay, create the sequence of partial sums. If the limit of the s of n's is some number as n goes to infinity, we write that the sum of the a sub k's from 1 equals infinity equals L, and say that the series and we say in English that the infinite series converges to L. So let me give you an example of just how we use this language. If I write summation 1 over k plus 3, k equals 1 to infinity equals 11/18. Okay. If I write this is a shorthand. Okay. This is a shorthand. What it's shorthand for is what we really mean. What that really means is that the sequence of partial sums Sn equals this converges to L. Okay. Right? Or what we just wrote, just now we wrote this thing equals 1. Right? Just now we wrote this thing equals 1. It doesn't mean that you can somehow, you have some sort of infinite arithmetic. It's rather that you translate this. What this means is that the sequence of partial sums S of n being the sum of these guys, and k equals 1 to n, converges to 1. Okay, and this is how we create a kind of infinite arithmetic. Okay. We create it by translating it into terms of infinite sequences. Is this making sense? Anybody? Let's do an example. Here is a sort of standard example. Geometric series, so-called geometric series. Okay. Okay. So it looks like something like this. Summation of r to the k from k equals 0 to infinity, where r is some fixed number. Where r is some fixed number. Okay. How many of you have seen this before? Anybody seen this before? Okay. Some of you, a couple of you have seen it. Okay. So this is basically, what you're asking is, in some sense, what is 1 plus r squared plus r cubed plus r to the 4th plus, etc. Okay, right. You're taking r to the 0, r to the 1, r squared, r cubed, blah, 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 and you're adding them all together, and you're wondering what you get. Okay, but the way we think about this is in terms of the sequence of partial sums. Okay, so let's look at the sequence of partial sums. Consider the sequence of partial sums. Okay, so S sub n is going to be the sum of rk from k equals 0 to n. Okay, in other words, it's 1 plus r squared plus r to the n. Okay, and we're wondering what S sub n converges to, right? We ask, what is the limit of the S sub n's as n goes to infinity? Okay, it turns out that we can obtain a formula for a sort of helpful formula for S sub n. In the following way, we say, well, S sub n is this thing 1 plus r to the n, right? If I multiply that by r, I get r plus r to the n plus r to the n plus 1. Ready? Okay. Now, if I subtract the lower equation from the upper equation, you see that I get 1 minus r times S sub n equals 1 minus r to the n plus 1. Right? Which, if r is not equal to 1, I can divide both sides and see that S sub n is going to be 1 minus r to the n plus 1 over 1 minus r. Okay, and let me write that up here since maybe some people can't see it. 1 minus r to the n plus 1 over 1 minus r. Okay, so that's, I obtained the formula for the nth term of the partial sum sequence, right? And you notice that if r in absolute value is smaller than 1, then what happens to the partial sum sequence as n goes to infinity? What happens to the partial sum sequence? As n goes to infinity, if the size of r is smaller than 1, and what happens to this r to the n plus 1? It goes to 0, right? So we end up with S of n will converge to 1 over 1 minus r. Okay. So we write that the infinite series r to the k from k equals 1 to k goes from 0 to infinity equals 1 over 1 minus r for r in absolute value less than 1. Right? This is what we write. I have some dust in my eye. I'm not crying. Okay. So, for example, if I ask you, what is 1 plus a half squared plus a half cubed plus et cetera, right? Well, you'd say, okay, well, that's going to be 1 over 1 minus r, right? Where r is this 1/2, right? And so you end up with 2. Which is basically what you figured out earlier, right? If you have 0, 1, 2, right? And we look at the partial sums. Well, we start at 1, we add a half, we add a quarter, we add an eighth, we add a 16th, and so on and so forth. And each time we get half the distance to 2. And what we're saying is that the limit of those partial sums is 2. Right, which is what you saw earlier, basically. Okay, so this is what we mean by an infinite sequence equaling a number, right? An infinite series equaling a number. Okay, if I write, we have some infinite series that equals some number. We don't really mean that you can somehow do an infinite arithmetic and add all those things at the same time. What we mean is that if you look at the sequence of partial sums, that sequence converges to L. Okay. When we say that this thing equals 2, we don't mean that you can somehow add them all infinitely at the same time, but rather we mean that if you look at the sequence of partial sums, that sequence of partial sums converges to 2. Okay. And this is the idea that allows us to create a consistent way of dealing with infinite sums. Okay, that's it for today.